Welcome to the course Stability Aspects of Structural Steel Design, Concepts and Applications. In this class, we will talk about generic equation for elastic plate buckling coefficient K. In the previous class, we derived the generic equation for plate, which is simply supported on all four edges with a uniaxial normal stress as described on the left hand side. Here the variation of load is given as Nx equal to N naught into 1 minus alpha into y by b, where alpha is the measure of stress gradient that acts across the width of the plate. So the critical load is given as N naught critical equal to K into pi square d by b square, where the elastic plate buckling coefficient K is defined as A by B plus B by A the whole square divided by 1 minus alpha by 2, which we have derived in the last class. Now, when it is subjected to uniform compression and assuming that it is a plate where the width of the plate is equal to the length of the plate, basically a square plate, we have A equal to B, and for uniform compression, we have alpha equal to 0. So the value of K is given as A by A plus A by A the whole square divided by 1 minus 0 by 2. So which gives rise to the value K equal to 4.0. So N naught critical is 4.0 into pi square d by b square. So the elastic plate buckling coefficient K is given as 4.0 in this case. Now when we apply the load such that there is a triangular stress gradient that is acting across the width of the plate, here the value of alpha equal to 1, and taking a square plate A equal to B, the value of K is given as A by A plus A by A the whole square divided by 1 minus 1 by 2. So the value of K becomes 8. So N naught critical equal to 8 into pi square d by b square. Now let's talk about a stress gradient where alpha equal to 1 by 2, which results in a value of N naught at the top of the plate and N naught by 2 at the bottom of the plate, as you can see on the picture on the right hand side. So taking a square plate again, A equal to B and alpha equal to 1 by 2, we have K equal to A by A plus A by A the whole square divided by 1 minus 1 by 2 by 2, which gives rise to the value of K equal to 16 by 3. So N naught critical is given as 16 by 3 into pi square d by b square. So if we compare this with the uniformly loaded case, which is triangular in nature, and it is 1.33 times for a load case where there is a stress gradient acting across the width of the plate, where the top of the load is N naught and the bottom of the load is N naught by 2, the increase in load carrying capacity is 1.33 times. Now basically what we understand is that when the load is actually half of what it is given for a triangular loading case, the load carrying capacity is doubled, as you can imagine, from the value of K jumping from 4 to 8. And similarly, when it is 3/4 of the load that is being applied, where alpha equal to 1 by 2, the load carrying capacity increases by 33%, as you can see here. This is considering all the four edges of the plate as simply supported. But if we compare an uniform compression with all the four edges as fixed, which we have previously derived, we can see that the load carrying capacity is 32 by 3 into pi square d by b square, which is N naught critical, as you can see on the left hand side of the picture. So there is a jump of 2.67 times compared to all four sides simply supported. Now let's talk more about the K for various support and loading conditions. So you can see that the generic condition is basically a stress gradient acting across the width of the plate, as you can see on the left hand side. The loaded edges are given and the unloaded edges are free. The loaded edges are subjected to stress gradient and unloaded edges are free, as you can see on the picture, which is nothing but an uniform compressive stress acting across the width of the plate, as you can see, plus the bending stress, as you can see on the rightmost side of the picture. A combination of uniform compressive stress plus bending stress gives rise to the stress gradient condition on the left hand side. So if we have to understand that in its entirety, we can explain that in the form of a table. As you can see here, the loading is given at the first column. The second column talks about the ratio of bearing stress to compression stress, which is sigma CB divided by sigma sub C, and the minimum buckling coefficient K sub C is given, which depends upon the loading conditions. Here we have assumed that the loaded edges are always simply supported and the unloaded edges are basically either simply supported or fixed depending upon the condition, and whose K values actually varies based on the loading conditions. Looking at the table again here, for the first case, the loading is basically uniform compression nature, where sigma 1 equal to sigma 2, as you can see here. So the ratio of bending stress to compressive stress is equal to 0 because the bending stress is absent in this one. So 0 divided by something is equal to 0, which leads to pure compression. The next one is the minimum buckling coefficient K sub C. Here we have already assumed that the loaded edges are simply supported. So when the unloaded edges are simply supported, which means that all four sides are simply supported, we have a value of k equal to 4.0. The next column talks about if the unloaded edges are fixed, the value of k is given as 6.97. The next column talks about when the unloaded edges are fixed. When the unloaded edges are fixed, the value of k is given as 6.97. The third column talks about the top edge being free. So when the top edge is being free, there are two conditions. The bottom edge can be simply supported or the bottom edge can be fixed. When the bottom edge is simply supported, the value of k is given as 0.43. To be precise, it is 0.425. We have rounded off to 0.43. When the top edge is free and the bottom edge is fixed, the value is 1.277 and we have rounded off to 1.28. Similarly, when the bottom edge is free and the top edge is simply supported, again the same values of k hold good here as well, which is 0.43, and when the top edge is fixed, we have 1.28. This is for a loading case when it is subjected to uniform compression and the loaded edges are simply supported, and depending upon the unloaded edges, we have different buckling coefficients, which is also given in the note below, which is values given are based on plates having loaded edges simply supported, and certainly it is conservative for assuming a fixed condition. Now let's look at the next case where it is subjected to pure bending. When it is subjected to pure bending, the top of the flange plate is subjected to sigma 1, the bottom is subjected to sigma 2, the top is subjected to compression, and the bottom is subjected to tensile forces. As you can see here, the compressive forces are represented by a red color arrow mark and the tensile forces are represented by a green color arrow mark. Since the value of compression is 0, here we have sigma CB divided by 0 becomes infinity. The ratio of bending stress to compression stress is sigma sub CB divided by sigma sub C, and here the compressive stresses are 0, so 1 by 0 becomes infinity. So this leads to a case of pure bending. The next column indicates when the unloaded edges are simply supported, the value of k is given as 23.9. When the unloaded edges are fixed, the value is given as 39.6. And when the top edge is free and the bottom edge is simply supported, we have a value of 0.85. And when the bottom edge is fixed, the value is given as 2.15. Again, all these values are based on assuming that the plates are simply supported along the loaded edges and they are conservative for fixed condition. Now, let us look at another condition where it is subjected to a triangular variation of load. As you can see here, basically the top of the plate is subjected to sigma 1 and the bottom value is sigma 2 is equal to 0. So, the ratio of bending stress to compressive stress is given as 1.0 here. And the minimum buckling coefficient is for unloaded edges simply supported is given as 7.8. When the unloaded edges are fixed, we have 13.6. Similarly, when the top edge is free and the bottom edge is simply supported, we have 0.57, and the bottom edge is fixed, we have 1.61. And for the case of bottom edge free and the top edge is simply supported, it is 1.7, and the bottom edge is free and the top edge is fixed, it is 5.93. Here we can see that when the values for top edge free and bottom edge free, the k values are very different. The reason being that the loading is not uniform, the loading is also different, and hence there is a change in the k value, which is not the same as in uniform compression. In uniform compression, the top edge free or the bottom edge free, the values of k were same because the loading conditions were the same. Here the loading conditions are such that the top of the plate is taking sigma 1, which is the maximum compressive stress, and the bottom is subjected to 0, and hence there should be a change in the k value depending upon the boundary conditions. So let's talk about the generic equation for elastic plate buckling coefficient k. For plates simply supported on all four edges, a generic equation for k is given by Peacock in 1987. The value of k sub c is given as 4 plus 2 into 1 minus psi the whole cube plus 2 into 1 minus psi, where the stress ratio psi is defined as minimum stress sigma 2 divided by maximum stress sigma 1. For the first case where it is subjected to uniform compression, the value of sigma 1 is equal to sigma 2, and hence the value of psi is given as 1. For the next case where it is subjected to bending, sigma 1 represents the compressive stress that is acting at the top of the plate and sigma 2 is the tensile stress acting at the bottom. The ratio is defined as minus 1 because sigma 2 is minus sigma 2. Sigma 2 and sigma 1 are the same, so sigma 2 equal to minus sigma 1 divided by the maximum stress sigma 1. So, we have minus 1 as psi. So, the next case is a triangular variation of load where sigma 1 is the stress that is acting at the top of the plate and sigma 2 equal to 0 as you can see here. So, 0 divided by sigma 1 leads to psi equal to 0. Now, for plates with one longitudinal edge free, a series of solutions for K were provided by Bamba and Rasmussen in 2004 from University of Sydney, Australia. You can see for the first case where the compression stress gradient free edge F2 is given by this diagram where F1 is the compressive stress, the maximum compressive stress, and F2 is the minimum compressive stress, and F2 is closer to the free edge. The value of K is given as 0.578 divided by psi plus 0.34. Whereas the compression gradient free edge is F1, we have that F1 as the maximum compression and F2 is the minimum compression, and you can see that F1 is closer to the free edge, and we have the value of K equal to 0.57 minus 0.21 into psi plus 0.07 psi square. And for the case of bending where the free edge is in compression, we have the value of K equal to 0.57 plus 0.21 into psi plus 0.07 psi square. Here F1 is the compressive stress that is acting which is closer to the free edge, and F2 is the tensile stress that is acting that is farther from the free edge. Now, for bending, when the free edge is in tension, we have the value of K equal to 1.7 plus 5 into psi plus 17.1 into psi square, where F1 is the compressive stress that is acting away from the free edge and F2 is the tensile stress that is acting closer to the free edge. Now, let us look at the elastic plate buckling coefficient for plates under in-plane shear. In the previous class, we have obtained the critical load for simply supported plate under shear loading, and we got the value Nxy critical equal to 11.1 into pi square d divided by a square, where K sub s is the shear buckling coefficient which we have derived using the strain energy method as 11.1. However, a more thorough examination by Steen and Neff obtained for the critical load Nxy critical equal to 9.34 pi square d by a square, which is shear buckling coefficient is given as 9.34, where d is the flexural rigidity of the plate per unit width given as E into h cube divided by 12 into 1 minus mu square, where E is the modulus of elasticity, h is the thickness of the plate, and mu is the Poisson's ratio. Solutions were also developed by Timoshenko in 1910, Bergman and Reisner in 1932, and Seidel in 1933 for a plate simply supported on all four edges. The value of shear buckling coefficient is given as 4 plus 5.34 divided by alpha square for alpha less than 1. Alpha is defined as the aspect ratio of the plate, which is the length of the plate divided by the width of the plate, and it is given as 5.34 plus 4 divided by alpha square for alpha greater than 1, which is very similar to what we see in section 8.4.2.2 shear buckling design methods as per IS 800-2007, where the shear buckling coefficient is given as 5.35 when transverse stiffness are provided only at the supports, and it is given as 4 plus 5.35 divided by c by d the whole square for c by d less than 1, and is equal to 5.35 plus 4 divided by c by d the whole square for c by d greater than 1.0, where c and d are the spacing of the transverse stiffness and depth of the web respectively. So, this equation is very similar to what we have seen on the left hand side developed by Timoshenko and other people, and similar equations are used in IS 800 as well. Thank you very much, and I look forward to meeting you in the next class.